Let's show that the capacitance of a parallel plate capacitor is given by the product of the permittivity of free space and the area of a capacitor plate divided by the separation distance between the plates. Well, let's go ahead and first illustrate what this setup looks like. So a parallel plate capacitor has two parallel conducting plates. One conducting plate has a charge of positive Q if the capacitor is charged, and the opposite plate will have the same amount of negative charge. These two plates are separated by a distance of d, and they each have an area A. Our goal is to figure out the ability of this parallel plate capacitor to store charge, and the measure of that ability we call capacitance. So to do that, let's start with the definition of capacitance. Capacitance is defined as the ratio of charge per unit potential difference. And if you look at this, you would see that the unit of capacitance is the coulomb per volt. 1 coulomb per volt is defined to be a farad. The farad is the unit of capacitance. So we're going to begin our proof by starting with this definition of capacitance. Now, first off, we don't know how much charge is on either capacitor plate. It seems like it would be important if it's part of our definition. Secondly, we don't know the potential difference between the plates. It wasn't given to us. So let's just start off by assuming that our plates are charged with charge Q. Now, if our plates are charged with charge Q, that means that there is going to be an electric field established between the upper and the lower plates. Now, because we're going to assume the separation distance is small in comparison to the distance between the plates, we could say that the electric field between the two plates is uniform, pointing from the positive plate down to the negative plate. Now, there will be some fringing on the edges, but we're going to neglect the fringing along the edges because we're going to consider the size of the plate to be very, very big, which will neglect any fringing of the electric field on the sides. Because there is an electric field that's established in the space between the plates, we do know one connection between electric field and electric potential, that the potential difference between 2 points in an electric field is equal to the line integral of that electric field, and rather it's equal to the negative of the line integral of that electric field. So at least we now have a connection between the potential difference of our capacitor, which we need that, and the electric field. Now here's the thing. We showed previously that the magnitude of the electric field in between the plates of a capacitor is equal to sigma over epsilon naught. So you know what? I think we have enough information to figure out how to solve for the capacitance. So in solving for the capacitance, I should remind ourselves that this definition, it is the magnitude of the charge over the magnitude of the potential difference. So we're going to, in effect, take the absolute value of the potential difference of whatever we find. So our task right now is to find the potential difference between the plates of the capacitor. And what I'm going to do is I'm going to start off with another picture to help me with the integral. Here's our upper plate. I'm going to exaggerate the separation distance. Here is the lower plate. And let's just do a couple electric field lines for illustration. Here's our electric field lines. We want to find the potential difference between these two plates. That potential difference, remember, and we'll find the magnitude. So that potential difference is going to be equal to the positive of the line integral of the electric field. So whatever we find the line integral of the electric field to be, we're going to have to take the magnitude. Now we need to figure out our points A and B. Well, let's define point A to be a point on the positive plate. So we'll take a point A to be maybe this point right here. That's point A. And point B, we're going to take it to be a point opposite that point A on the bottom plate. Now, in order to evaluate this line integral, we need a line to integrate along. So we're going to take a path directly from point A to point B. Here is our path, and we're going to look at a tiny bit of displacement on that path. That tiny bit of displacement is going to be given as dr vector. So point B is a distance of d away, so I'll just label that as b equals d. And we now have our coordinate system. Our coordinate system is just the coordinate system of the line, where our origin is where we start, and we're just going to integrate along that line until we get to point B, which, I really probably should have originally called point B D, but that's okay. So this allows us to set up the line integral from A to B, which is from 0 to D, of the electric field. Well, the electric field has a magnitude of sigma over epsilon naught. And notice the electric field is in the direction of our displacement differential. So I will indicate that the electric field then is sigma over epsilon naught r hat, where r hat is the unit vector that's in the direction of our displacement. And remember, dr, our displacement differential, is just going to be given as dr r hat. So what we have here is for our change of potential, and let's remember we're going to just evaluate the magnitude of this later. So for our change of potential, this is going to be our electric field, which is sigma over epsilon naught r hat, dotted with dr r hat, and this is just essentially sigma over epsilon naught dr, and then it is the dot product between the r hat unit vectors. Now remember, a unit vector has a magnitude of 1, and the dot product of a unit vector with itself is equal to the magnitude of that vector squared. So the magnitude of 1 squared is just 1, and now we have the change in electric potential between the 2 points is equal to the integral from 0 to d sigma over epsilon naught dr. Well, sigma over epsilon naught is a constant, and we have the integral from 0 to d of dr. When we integrate this, this is sigma over epsilon naught r, evaluated from 0 to d. And finally, we have the magnitude of the potential difference is equal to sigma over epsilon naught d minus 0, which is just sigma over epsilon naught d. Well, that's great. We have now found an expression for the magnitude of the potential difference between the two plates of our capacitor. It's equal to sigma d over epsilon naught. So, remember, the capacitance is just defined as the magnitude of the charge on the plate over the magnitude of the potential difference between the plates. So that means that the capacitance is equal to Q over sigma d over epsilon naught. Or the capacitance is Q for the charge, epsilon naught over sigma d. Okay, so we're getting closer. Remember, we needed to show that the capacitance for a parallel plate capacitor is equal to the product of the permittivity of free space and the area of capacitor plate over the separation distance. Well, I see that we have our epsilon naught and we have our d separation distance, but unfortunately, we don't know how much charge is on the plates. And remember, the charge on a capacitor plate will vary depending on how much potential difference we put across the plate. So there isn't one amount of charge on the plate. And so the surface charge density, sigma, will also vary. Well, let's have a little faith. I'm thinking that the charge is probably going to go away. Well, why am I thinking that? The surface charge density on either plate is uniform. Remember, surface charge density is defined as charge per unit area. Now, if the density is uniform, that could be given as the total charge over the total area. So rearranging this says surface charge density times the area is equal to the charge on a plate. Well, let's plug that into our expression for capacitance. So we get capacitance is equal to charge Q, which is equivalent to surface charge density times the area of a plate. This is multiplied to the permittivity of free space divided by the surface charge density and the separation distance between the plates. And look at this. The surface charge density cancels. This gives us our result for the capacitance of a parallel plate capacitor. It's given as the product between the permittivity of free space and the area of a capacitor plate divided by the separation distance between the plates. And here's a thing that you should notice. This capacitance does not depend on the charge on the plate. And that's a good thing because we want to be able to know the capacity of our capacitor to be able to store charge. So here we're seeing that the capacitance doesn't depend on the charge on the plates. Our capacitance also doesn't depend on the potential difference between the plates. The only thing the capacitance depends on here are the size of the plates and the separation distance of the plates. So this suggests that capacitance only depends on the geometry of the capacitor, not on the charge stored by the capacitor or by the potential difference.